Welcome to this video. Today, we'll be solving a fascinating problem titled Short Encoding of Words, which is problem number 820. This problem challenges us to think critically about encoding multiple words efficiently. Let's dive in and explore the approaches to tackle this problem. In this problem, you are given an array of words, where each word is made up of lowercase English letters. The goal is to encode these words into a single string in a way that minimizes the total length of the string. To encode a word, you append a special character, the hash symbol hashtag, to the end of the word. For example, the word time becomes time hashtag when encoded. A word is considered encoded within the string if the string ends with the encoding of that word. Your task is to find the shortest possible string that can encode all the words in the array, and return the length of this string. The input includes a list of strings called words, and the output will be an integer representing the length of the shortest valid encoding. This problem challenges us to find an optimal solution by identifying overlaps or redundancies between the words in the list. Let's look at an example to understand this better. Suppose the input list of words is time, me, bell. A valid encoding for these words would be the string time hashtag bell hashtag. Here, me is encoded within time hashtag because the string time hashtag ends with me hashtag. Similarly, the word time is encoded explicitly in the string. The overall length of this encoding string is 10, which is the shortest possible encoding for this input. This demonstrates how overlapping words can reduce the total encoding length by avoiding redundant representations. Now, consider a simpler example. If the input list contains only the word T, the shortest valid encoding would be T hashtag. Since there's only one word, no overlaps are possible, and we simply encode the word followed by the hash symbol. The total length of the encoding string in this case is 2. This highlights that when there's only one word, the encoding is straightforward and minimal. Let's explore a more complex scenario with the input, time, me, IME, bell, L. Here, a valid encoding would still be time hashtag bell hashtag. The word me is encoded within time hashtag, and IME is also encoded within time hashtag. Similarly, L is encoded within bell hashtag. This encoding captures all the words while avoiding redundancy. The total length of this encoding string is 15. The constraints of the problem ensure that the number of words and their lengths are manageable, and edge cases like duplicates or overlapping prefixes and suffixes are important to consider. For example, duplicates do not increase encoding length, and the longest word in a set of overlapping words will dictate the encoding. These rules help guide the solution to achieve the shortest possible encoding length efficiently. To solve the problem of encoding words with minimal total length, we first consider a brute force approach. Here, the idea is to generate all possible encodings by checking each word to see if it is a suffix of any other word in the list. If a word isn't a suffix, we add its length plus 1 for the hash symbol to the total encoding length. While this method is intuitive, it's highly inefficient for large inputs due to the nested iterations required to compare all word pairs. The time complexity of this approach is O, n squared asterisk k, where n is the number of words and k is the average word length, making it impractical for larger datasets. Next, we look at an optimized approach involving sorting the words by length in descending order. By processing longer words first, shorter words can be checked as potential suffixes of these longer ones, reducing redundant comparisons. A set is used to store unique encodings, and we only add words that are not already a suffix of an existing encoded word. While this method improves efficiency, reducing redundant suffix checks, it still involves sorting the words, which adds an O, n log n, overhead, and suffix checks for all words in the worst case still require O, n asterisk k. Finally, we explore using a tree, or prefix tree, which is the most efficient approach. In this method, we reverse the words and insert them character by character into the tree. Reversing the words transforms suffix relationships into prefix relationships, making it easier to manage. If a word creates a new path in the tree, it contributes to the total encoded length. This approach avoids repeated suffix checks, with a time complexity of O, n asterisk k, for constructing the tree and a similar space complexity to store it, making it highly efficient for large inputs. Given the various approaches discussed, the tree-based method stands out as the most efficient and scalable solution. By reversing the words, it transforms suffix relationships into prefix relationships, allowing the tree structure to handle them effectively. This eliminates unnecessary comparisons and ensures that the encoding length is calculated optimally. Compared to the brute force and sorting methods, the tree approach not only reduces computational overhead but also provides a clearer, more structured way of solving the problem. There are important trade-offs to consider. The tree-based method is highly efficient, minimizing redundant checks and performing well with large datasets. However, it does require additional memory to store the tree, which scales with the input size. While the implementation is slightly more complex than the sorting approach, the performance benefits outweigh this added complexity. Overall, the tree approach achieves an excellent balance between time complexity and correctness, making it the ideal strategy for solving this problem efficiently and effectively. The problem we're solving is to find the minimum length of a single string that can encode all the given words, where each word is represented as a suffix followed by the hashtag character. The key challenge is to avoid redundancies, ensuring that no word in the list is a suffix of another, which would otherwise lead to unnecessary duplication in the encoded string. To start with a brute force approach, we take the list of words and parse the input. For example, if the input is words equals time, me, bell, we then generate all possible encodings by iterating through each word and comparing it with every other word in the list. During this process, we check whether one word serves as a suffix of another, using Python's ends with method. For instance, we can check if me is a suffix of time. This forms the foundation of our initial brute force solution for the problem. After identifying potential suffix relationships, the next step is to filter out redundant words. If a word is determined to be a suffix of another, it is marked as redundant and excluded from further consideration. We maintain a set of unique words that are not suffixes of any other words. Once we have this reduced set of unique words, we calculate the total encoded length. For each unique word, we add its length and include an additional one to account for the hashtag character that follows each word in the encoded string. Finally, we sum up these lengths to determine the total encoding length and output this value as the result. While this brute force approach is functional, it is computationally expensive, especially for larger inputs, which motivates the need for optimization. To optimize the solution, we use a tree, also known as a prefix tree. This data structure allows us to efficiently handle the suffix relationships by leveraging a key transformation. First, we reverse all the words in the input list. For example, reversing words equals time, me, bell results in words equals emit, leb. By reversing the words, we turn the suffix checking problem into a prefix checking problem, which is much more straightforward to handle using a tree. Next, we insert these reversed words into the tree, character by character. Each new branch created in the tree represents a unique suffix in the original space, and only these unique suffixes contribute to the encoding length. This approach is significantly more efficient as it avoids the need for pairwise comparisons. Once all words are inserted into the tree, we traverse it to calculate the total encoding length. Each unique path in the tree corresponds to a unique suffix, and for each such path, we calculate its length and add one for the hashtag character. The resulting sum gives us the total encoding length. This optimized approach is not only faster but also highlights some key insights. By reversing the words, we simplify the problem from suffix checking to prefix checking, which aligns well with the structure of a tree. The tree ensures that only unique prefixes or equivalently, unique reversed suffixes are stored, eliminating redundant comparisons. Furthermore, since only words that create new branches in the tree impact the encoding length, we achieve a minimal and non-redundant encoding. To implement this solution, we rely on two key data structures. First, the tree is used to store the reversed words efficiently. Each node in the tree represents a character, and together, the paths represent unique suffixes from the original input. Second, a set is used in the brute force approach to keep track of unique words. When comparing the two approaches, the complexity analysis reveals the efficiency of the tree-based solution. The brute force method has a time complexity of n squared asterisk k, where n is the number of words and k is the average word length, as every word is compared with every other word. Its space complexity is n. On the other hand, the optimized tree approach significantly reduces the time complexity to n asterisk k, as each word is processed only once during insertion and traversal. The space complexity is n asterisk k, which accounts for the memory required to store the tree. To understand how these approaches work, let's walk through an example with the input words equals time, me, bell. Using the brute force method, we start by comparing each word with the others. We find that me is a suffix of time, so we mark me as redundant. The word bell is unique and remains in the set. Thus, the resulting unique words are time, bell. To calculate the encoding length, we sum the lengths of these words and add 1 for each hashtag character. The total encoding length is len, time, plus 1 plus len, bell, plus 1 equals 10. While this approach works, it illustrates the inefficiencies of comparing each word with every other word. Now, applying the optimized tree-based solution to the same input, we first reverse the words, resulting in words equals, emit, leb. We then insert these reversed words into the tree. Inserting emit creates new branches, contributing to the encoding length. When inserting no new branches are created, as is already covered by the emit path. Finally, inserting leb creates new branches in the tree. The total encoding length is calculated as the sum of the lengths of the unique paths in the tree, plus 1 for each hashtag character. This results in 4 plus 1 plus 4 plus 1 equals 10. The output matches the brute force result, but the tree approach achieves this more efficiently by avoiding redundant computations. This Python implementation solves LeetCode problem number 820, short encoding of words using a combination of sets and suffix elimination for efficiency. First, all duplicates are removed from the input list by converting it into a set, ensuring only unique words are processed. Next, for each word, we iterate through its suffixes, from index 1 onwards, and remove any suffixes that exist in the set. This ensures that no word in the set is a suffix of another. Finally, the length of the encoded string is calculated by summing the length of each remaining word plus 1, to account for the hashtag character. This approach is efficient and ensures the minimum possible encoding length is achieved. This is the complete Java implementation for LeetCode problem number 820, short encoding of words. The logic mirrors the provided Python solution, with adjustments for Java's syntax and structure. Key differences include using a hash set for unique words and leveraging Java's substring method to remove suffixes. The code iterates through the array to filter suffixes efficiently and calculates the total length of the encoded string by summing the length of each unique word plus 1 for the hashtag character. The solution is concise and leverages Java's standard library effectively. To solve the problem, we start by removing any duplicates in the input list of words. This ensures that we work with a unique set of words, avoiding unnecessary repetition in our calculations. For the input words equals, time, me, bell, we convert it into a set, resulting in unique underscore words equals, time, me, bell. Next, we remove any word from this set that is a suffix of another word. For the word time, its possible suffixes are ime, me, and e. Since me is present in unique underscore words, we remove it, leaving unique underscore words equals, time, bell. For the word me, the only suffix is e, which has no impact as me is already removed. Finally, for the word bell, the suffixes are l, ll, and l, none of which are in the set, so no action is needed. The result is unique underscore words equals, time, bell. Now that we have the final set of unique words, we calculate the total length of the encoded string. For every word in unique underscore words, we add the length of the word plus 1 to account for the hashtag character that separates the words in the encoding. For time, the calculation is len, time, plus 1 equals 5. Similarly, for bell, it is len, bell, plus 1 equals 5. Adding these together gives a total length of 5 plus 5 equals 10. Therefore, the output for this example is 10. In the second example, we begin again by removing duplicates to create a set of unique words. Given the input words equals, t, time, a time, time, the resulting unique underscore word set is, t, time, a time, time. Next, we remove any word that appears as a suffix of another. Starting with t, it has no suffixes, so no changes are made. For time, its suffixes are ime, me, and e, none of which are present in the set, so again no changes are made. Looking at a time, its suffixes include time, which is in the set, so time is removed. This leaves unique underscore words equals, t, a time, time. Finally, for time, the suffixes are time, ime, me, and e, none of which are in the set, so no further changes are needed. The final set is unique underscore words equals t, a time, time. With the final set of unique words determined, we calculate the encoded string length. For each word in unique underscore words, we add the length of the word plus 1 for the hashtag character. For t, this calculation is len, t, plus 1 equals 2. For a time, it is len, a time, plus 1 equals 6. Similarly, for time, it is len, time, plus 1 equals 6. Adding these values together, we get 2 plus 6 equals 14. Therefore, the output for this example is 14. In the third example, the input is a simple list of single-character words, words equals A, B, C. After converting this list into a set, we obtain unique underscore words equals A, B, C. Since each word is a single character, none of them can be a suffix of another. Thus, no words are removed during the suffix removal step, and the set remains unique underscore words equals A, B, C. We then proceed to calculate the encoded length. To find the total encoded string length, we sum up the length of each word in unique underscore words plus 1 for the hashtag character. For A, the calculation is len, A, plus 1 equals 2. Similarly, B is len, B, plus 1 equals 2, and C is len, C, plus 1 equals 2. Adding these together gives 2 plus 2 plus 2 equals 6. The output for this example is 6. To analyze the time complexity of our solution, we first break it down into distinct steps. In step 1, we remove duplicates by converting the input list of words into a set. This process requires iterating over all the words and inserting them into the set. Since inserting a word of length L into a set takes O(L) time, the total cost of this step is proportional to the sum of all word lengths, which is O(N), where N represents the total number of characters in all the words. Next, in step 2, we focus on removing suffixes. For each word of length L, we generate all possible suffixes starting from the second character, which involves running an inner loop approximately L1 times. Removing each suffix from the set using the discard method takes O(L) time on average, where L is the suffix's length. When we consider all words, the total number of suffixes generated is at most N, and the cost of processing these suffixes remains O(N) on average, even in the worst-case scenario where all words are unique and evenly distributed in length. In step 3, we calculate the length of the encoded string by summing the lengths of all unique words in the set. This operation is proportional to the total number of characters in the unique words, which also amounts to O(N) time. When we combine all these steps, the overall time complexity of the solution is O(N) on average. Even in the worst case, where all words are distinct and share no common suffixes, the time complexity remains O(N), because each operation scales linearly with the total number of characters. Moving on to space complexity, the input list words requires O(N) space to store all characters. Additionally, the set unique underscore words holds at most W unique words, where W is the number of words in the input. The space required for this set is proportional to the total characters in the unique words, which is again at most O(N). Temporary variables, such as the suffixes generated during step 2, do not require additional memory beyond the input size, as they are created and discarded during processing. Therefore, their impact on space complexity is minimal. Combining all these components, the overall space complexity of the solution is O(N), as the space used by the unique underscore word set dominates. To put this into perspective, let's compare the current solution with a naive approach. A brute force method would involve generating all possible encodings of the words, checking for redundancies, and selecting the shortest encoding. This process would require exponential time, specifically O(2 to the power of W, where W is the number of words, making it infeasible for even moderate input sizes. In contrast, the optimized approach efficiently removes suffixes in O(N) time and space by leveraging hash sets. This eliminates the need for explicitly generating or comparing encodings, making the algorithm far more practical and scalable. Now, let's summarize the best, average, and worst-case scenarios. In all cases, the time complexity is O(N), as the algorithm's performance is determined by the total number of characters across all words. Similarly, the space complexity is also O(n) in all cases, since the memory usage is directly proportional to the input size and the unique words stored in the set. This consistent linear performance in both time and space, regardless of the input structure, highlights the efficiency of the solution and its ability to handle large inputs effectively. When tackling this problem, there are a few common mistakes to watch out for. First, confusing suffixes with substrings is a frequent error. Remember that a suffix must appear at the end of a word, while substrings can occur anywhere. If you treat substrings as suffixes, you'll end up with incorrect results. Next, processing words without sorting them by length can also lead to issues. By handling shorter words before longer ones, you might exclude shorter words prematurely. Sorting the words in descending order by length ensures that longer words are checked first, which is crucial for accurate results. Another pitfall is failing to remove duplicate words or skipping the use of a set for lookups. This omission can result in redundant operations and unnecessarily increase the time complexity. Lastly, be sure to account for edge cases, like an empty list, a single word input, or words that share the same suffix. Overlooking these scenarios can cause runtime errors or incorrect outputs, which can be problematic in interviews or testing environments. Another frequent mistake is miscalculating the encoding length by forgetting to include the hash symbol, hashtag, in the count. The hashtag is a critical part of the encoded string, and ignoring it will lead to underestimating the length and producing incorrect answers. Now, let's move to some key insights for interviews. Sorting the words by length in descending order is a powerful optimization. It simplifies the process of identifying and excluding shorter suffixes, making your approach more efficient. Additionally, recognize that problems involving suffixes or substrings often benefit from techniques like sorting, hashing, or using a tree. In fact, using a tree is one of the most efficient methods for solving this problem, with a time complexity of O(n*L), where n is the number of words and L is their average length. It's also important to communicate your thought process during interviews. Explain why you're sorting the words or choosing specific data structures like a tree. This demonstrates a clear understanding of trade-offs and conveys your reasoning effectively to the interviewer. This problem is also connected to several related challenges that you might encounter. For instance, LeetCode 208, which involves implementing a tree, shares commonalities with this problem due to its reliance on prefix or suffix relationships. Similarly, problems like LeetCode 5, longest palindromic substring, and LeetCode 14, longest common prefix, also deal with string manipulation and efficient ways to find relationships between substrings. Now, let's discuss alternative approaches to solving this problem. The brute force method, while simple to understand, involves a time complexity of O(n²L). This is because for each word, you would need to compare it against every other word, which quickly becomes inefficient for large inputs. On the other hand, the tree-based solution is much more efficient with a time complexity of O(n*L). While it requires additional memory to store the tree structure, it provides a streamlined way to manage suffix relationships, making it a robust choice for this problem. Another effective approach to solving this problem is by using a hash set. This method also has a time complexity of O(n*L), similar to the tree-based solution. While it's generally easier to implement than a tree, it may be less intuitive when dealing with suffix relationships. That's because a hash set doesn't inherently provide the hierarchical structure that a tree does, which can make certain operations slightly less straightforward. However, for many use cases, the simplicity of a hash set makes it a practical and efficient choice. Ultimately, the best approach depends on your familiarity with these data structures and the specific constraints of the problem you're solving. Great job! In this session, we tackled the short encoding of words problem and explored both brute force and optimized approaches. Remember, understanding when to use data structures like trees can be a game changer. If you enjoyed this, please like, share, and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!